Okay, so we were discussing about the properties of the discretization. We started with consistency, then we started with transportiveness, then we talked about conservativeness, and next, now, today we'll talk about stability. So when you call a particular discretization a stable discretization, okay, so that is a question. When we call a particular discretization a stable discretization. Okay. So there is a condition if the error if the error in the solution variable do not grow variables do not grow abruptly or they do not become unbounded, then the discretization or scheme then the discretization or scheme is stable scheme. Otherwise, it is unstable. It is unstable. Okay. So the thing is, we should have this error in the solution variable should not grow abruptly or it should not be unbounded. So solution variables like u, v, w. So the solution at ith point and nth time should not grow with respect to time. N plus 1, you should not have the different values. I mean, there will be change, but suppose this value is 5 and this value is becoming 500. So this is a very abrupt change from one time to another time. So such a large changes or abrupt unbounded changes should not be there. And suppose n plus 2 is there and again it is making something like 1 lakh or 1 million something, then it is unbounded. It is unboundedly increasing. Okay. So if such a behavior is there, it is not a normal behavior, it is a unstable behavior. Okay. So for example, if you consider this our wave equation del u by del t plus constant speed a del u by del x is equals to 0. Now in this case, what do you mean by error should not grow? That I would like to show you by a picture. So in this case, we know that our this is our time axis and this is our x-axis, and in this case, for this a is equal a positive, we know that there is a one characteristic, and that characteristic is right running characteristics. Okay. So let me also make some time axis at particular time x-axis. So say this is a t is equals to 0, and this is t is equals to 1, and t is equals to 2. And let me focus on nth time, present time, known time plus unknown time. Now this is unknown, this is a known. Okay. And these are our grid points, grid locations. And we know that by the property of this characteristic, they should ideally pass through these points. It is like this point is shifting in time, this point is shifting, this point is shifting. So every time the solution, so suppose the solution at this here, the solution here is of this nature, for example, if this is the solution here, okay, and this value is delta, suppose, then every other place, at every other place, this solution will just shift. It will remain delta only. Okay. Now, in such a case, this is a stable case. This is a stable case. What is happening is this, in this stable case, u at I, n plus 1 divided by ui n is a, that ratio is is not changing too much. If this ratio amplitude is changing very, now this you can say amplitude, isn't it? Amplitude of the variables. Okay. So if this amplitude is very high, it means that suppose it is 100, for example, then ui at n plus 1 will be 100 times ui n. So it is abruptly changing. If it is 1 or some sort of, then it is a stable. Okay. So unstable and not growing. And this is the delta t, just to make it complete. And these are our delta x's. Now there can be other picture also in which you may get unstable solution. So unstable solution will be second time you may get diffusion also, you may get little diffusion also, and maybe increase like this, or maybe increase of this nature. Okay, so if this is the behavior, this white one is a unstable behavior. Okay, this is white one is unstable behavior. Let me redraw somewhere else so that you do not get confusion. So suppose initial solution here is delta, then this may be twice delta, or this may grow abruptly. So this is an unstable case. And there can also be a third case. There can also be a third case where it is possible to have okay. Here your initial solution may be delta, and then at later stages it can be little smaller than delta. That is also possible. Smaller than delta is possible. Okay. So in that case, here there is no growth. Here there is no growth. Okay. Here also there is no growth. Here there is a growth. Okay. This is growing. Error is growing. Error is growing. Here no growth of error. Growth of error. Here error is not growing, not growing. Okay. But the solution is getting diffused. Initially it is delta. This is small 0.75 delta or something like that. But still this is okay. Still this is a stable case. Because by the definition of stability, the solution should not become unbounded. Okay? It should not become unbounded. Okay. Now, for getting this particular situation and this particular situation and not this condition we have to avoid, what should be, what should be the condition? Okay. So the getting these particular solutions is dependent upon what delta t you choose, what delta x you choose, and the speed at which you are moving. Because you see, what is happening is that this characteristic curve, this characteristic curve is passing through all the points. Okay, these next points, and your solution is supposed to move from this point. Suppose I say this is I minus 1 point. At nth time, it should move to n plus 1th point in at ith location. This point should move at n plus 2 time at I plus 1th location. Likewise, I plus 2th location. Now, when it is moving, moving means it is moving with velocity u. It is moving with velocity u, isn't it? It should be moving with that velocity. So, this distance, I'll calculate this distance. Okay, distance divided distance, and that velocity divided by time, in time step in which you are moving, this delta t will decide what is a u, or u will decide what is delta either delta t or either delta x. If two values are known, you know that. So we see that these three parameters decides how my solution is moving. How my solution is moving. Now, what values of these will make such a way that they do not move, in an abrupt manner, or there are no changes abruptly. So the condition should be lying on these things, these coefficients. Okay, these coefficients. So look at, let us look at this condition. So the governing equation for this is our this wave equation. So we'll write again here that wave equation here. Del u del t plus a del u del x is equals to 0, and we'll now describe this by a scheme ui n plus 1, right? Ui n divided by delta t plus, now which scheme we should use? Backward, forward, or central? Because this is a right running case, a positive, so we should use backward difference. So I'm using backward difference ui minus 1 n delta t equals to 0. Okay.
So,
Now this choice of n is a random. Now we are taking just n. Okay, so this choice is random. We'll see later if we change n to n plus 1, what is going to happen. But right now we are not focusing on that. Right now we
so
focus
one
on
doubt.
this. Okay, and for this particular formulation only, we will get a condition. For other formulation, we do not get a condition. So we should bother only about this n case, not n plus 1 case. Okay. So here now I can write this uin plus 1, we can write as uin. This unknown will be expressed in terms of known. This is known, this is known, this is known, this is known. So unknowns are expressed in terms of known plus a delta t delta x ui n minus ui minus 1 n. Okay. Or let me also write like ui n plus a delta t delta x ui n minus a delta t delta x ui minus 1 n. Now, as per this condition, what do you want? Our solution should be moving from this I minus 1 to I, and that condition can come only when these particular coefficients become 1. Suppose this become 1, then I get uin plus uin minus ui minus 1 n. Okay. Uh, Here it should be minus, isn't it? Here it should be minus. And this should be a plus. So this is plus, this is minus. So what do we see here is finally ui n plus 1 should be equals to ui minus 1 n. Okay. And that is exactly happening here. Whatever value of ui n plus 1 is there, this value here n plus 1 is equals to ui minus 1 n. That is happening only when we are taking, this is happening, this is possible only when a delta t delta x is equals to 1. Also, now for a damping case, if this particular thing is lesser than, So here you see ratio un plus 1 and ui minus 1 n, that will become 1. Now, if I want this ratio less than 1, not more than 1, then I can say also that A delta t should be, delta t delta x should be less than or equal to 1. So, this is a more general condition, and this condition is called as, this condition is a Courant-Friedrich-Lewis condition, CFL. Courant-Friedrich-Lewis condition. CFL condition, CFL condition. Okay. So if this is the thing, you have to take A such a way, A delta T and delta X such a way that this ratio should be always less than equal to 1. Then only this particular discretization will give you a stable solution. Okay. If this condition is satisfied, if this condition is satisfied, then only the discretization will give you the scheme. The scheme will give a stable solution. Okay, otherwise it will be unstable. Now suppose let us consider another example with a diffusion equation. This was a hyperbolic equation. Second example, suppose we take del u del t is equals to alpha del 2u del x square. This is our parabolic equation. Okay. Now let us take a discretization of this ui minus uin delta t and is equals to alpha u I plus 1 minus ui plus ui minus 1 and all are at n and delta x. So if I express this into in terms of ui n plus 1, it should be looking like ui n plus alpha delta t delta x and will be now writing properly minus alpha delta t delta x uin plus alpha delta t delta x ui minus 1 n. Okay. Now suppose in this case this term goes 1, this term goes 1 and this 1, then you are likely to get uin plus ui plus 1 and minus uin plus ui minus 1 n. And what do we see? These two terms will get cancelled and you get ui plus 1 minus ui minus 1 and both are at nth level. So what you are seeing here is this is a time domain, this is a space domain, and this is our x domain. And here at every time we have these characteristics. So this is one characteristic, this is second characteristic, third characteristic. And what do you know that suppose I am talking about this as n plus 1 unknown and this is a known. So whatever the values below this n plus 1, that is a domain of This is a domain of dependence. Okay, domain of dependence. So I'm talking about, we are talking this ui n plus 1. This is a ui n plus 1 value, and this ui plus n plus 1 value for this particular ratio is dependent upon these values, u I minus 1 n and u I plus 1 n. Okay, and not any other value here, not any other value over here. So what we are saying, suppose the value of ui and ui minus 1 is some value. Suppose now this is a value. This is a value delta, and uin minus 1 value is twice delta. Then total value at uin should be ui plus 1 minus n. This should be delta, isn't it? According to this, it should be delta. Suppose alpha delta t delta x becomes a large number. So you will get some ratio here, which will be a large number. In that case, you will also get a some value here, some value will come here, and that will not add up to, suppose you get some value here, that will not add up to a particular proper behavior here. It will give you some, sorry, this is a plus. Okay, so this is a 3 delta. This is 3 delta. This is plus, right? This is plus. This is 3 delta. This is physical, because suppose we have a temperature, suppose here 100 degree, here 100 degree, then the temperature here should be 200 degrees rather than having some unphysical values of the temperature there. If you have this value also 100 plus 100 plus 100 or 100 plus 100 minus 100, then here the value will be different. Uh, and those may lead to some unphysical results, because this value may be very higher with the addition of these alphas and these things, because here there is no coefficient, here there is a coefficient which will be reducing from this uin value, and it will have some magnitude here that will add up, and it will increase the value unnecessarily. Okay, so for this, we can say this is a quite good, because all values ui depending on all known values. Okay, below that, suppose this is n plus 1, then all values will be known from this side. So this condition alpha delta t, okay, I made a mistake here. I made a mistake. What is that? I made a mistake here. Yeah, it should be twice, and this should be delta x square. 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 And since this is twice, now we have to say it is 1 by half, 1 by half, 1 by half. Okay. So this says like it should be uh, average of that. Okay. This should be 1 by half, and this is 1 by half. So that will become 1 and will cancel out. Okay, now it is correct. So alpha delta t delta x square should be either 1 by 2, or it is good if we do not see any large values of uin plus 1. These large uin plus 1 only will not be possible when alpha delta t delta square should be less than half. If these values are lesser values, then they will not add up too much in uin plus 1 to make it unstable or unbounded. What we want here is at n plus 1, ui n plus 1, our values from the previous should not change abruptly. They may decrease. Okay, that diffusion is okay, but abrupt increase is a problem. So it can also be less than half. So condition for this parabolic problem becomes alpha delta t, delta x square should be less than equal to half. Suppose there is a one more term here, alpha delta 2u delta x square, then what will happen? Then we will say that this condition delta x square alpha delta t delta x square plus alpha delta t delta y square should be less than equal to half. And suppose we have delta x is equals to delta y. Suppose delta x is equals to delta y, then alpha delta t delta x square should be less than equal to 1 by 4. Okay. If in 2D, suppose a 3D problem is there. In 3D, if delta x is equals to delta y is equals to delta g, then they will add up. One more term will be add up. So alpha delta t square delta x square plus alpha delta t square delta t delta y square plus alpha delta t delta z square. This should be equals to price. So that 3 alpha delta t delta x square should be less than equals to half. So alpha delta t delta x square should be less than equals to 6. Okay. So 1 by 1, 1 by 2, 1 by 4, 1 by 6. These are the conditions for stability. Okay. Condition for stability. So parabolic equation has this condition alpha delta t delta x square should be less than equals to half, or alpha delta t delta x square should be less than equals to 1 by 4, or alpha delta t delta x square should be less than equals to 1 by 6. Okay. So this is about stability. So these conditions we should satisfy. Alpha delta t delta x should be less than equal to 1, or and alpha delta t delta x square should be less than half, 1 by 4 or 1 by 6. Okay. So when your combination of suppose we have equation like this, plus u del u del x is equals to alpha del 2u del x square, then both the conditions are there. U delta t delta x should be less than equal to 1, and alpha delta t delta x square should be less than equals to half. So you have to select delta t delta x values such a way that these conditions will get satisfied for this particular problem. Then only this problem is stable or stability. For stability, above conditions must be satisfied. Must be satisfied. So suppose now we talked about so finish here. So we talk about number one, that well posed problem. You know that, right? A well posed problem is the one where the any change in the boundary conditions will not give you large changes in the solution. Any small change in the boundary conditions will not give you the large change in the solution of the problem, then the problem is well-posed problem. Second, we have seen that what is a consistent scheme. So a scheme is a consistent when delta x, delta t, delta y, delta g, these grid parameters are becoming very small. Then you essentially convert discretize versions very close to the partial differential equations. Okay. And now we have seen what is a stable scheme. So any scheme where this combination of delta t and delta x is such a way that it satisfies certain condition, then it is a stable scheme. Now, if all these three conditions are satisfied, if there is a well-posed problem, if the problem is well-posed problem, plus it is a consistency, consistent, and if it is a stable, then it is guaranteed that we get a convergence. Convergence means we get a solution, correct solution. Okay. So if these three conditions are satisfied, if problem is well posed, the scheme is consistent, and the scheme is stable, you are going to get a solution. Okay. You should get. Okay. So that is called as a theorem. So we will write here for a well posed problem, well posed initial value problem, we'll say now initial value problem. A consistent finite difference method is convergent if and only if and only if the method is stable. If the method is not stable, okay, if it is a well posed and consistent and method is not stable, you will not get solutions. And this theorem is called as Lax theorem, Lax equivalence theorem.
Sir, sir,
Okay, so these things should be satisfied, and so Lax. Okay, now we'll move on to next.
hello, sir.
Now suppose these are x and we are moving in a time. Okay, now this is 0, 1, 2, like that. Now if I want to use a scheme here, what scheme I should use? This is a delta t. What scheme should I use for del u del t? What scheme should I use for del u del t? Is it forward difference? Should it be backward difference or should it be central difference? Which one it should be? Hello?
Sir, hello. Sir, am I audible, sir?
Yeah, Viknesh. I'm not able to hear you.
Sir, I have unmuted, sir, but
Speaker is off. Yeah, Viknesh.
hello, sir. Yes, am I audible, sir?
Yes, yes, yes.
Yes, sir. Actually, I wanted to ask that we solved in the two class before we solved that beta delta x problem, no, sir. One side it
Mm-hmm.
was delta x and beta delta x.
Mm-hmm.
So that will come under unstable condition, no, sir.
Why?
Because the delta x difference is uneven, no, sir. One side it is delta x and the other is beta times delta x, no, sir. So it will be that increasing diagram that you draw that you draw you drew that in the before slide, sir.
Yeah, but was there a time involved in that? In deriving those equations, was
Yes,
there a
sir.
time involved?
No, sir.
No, sir.
No. Okay. So don't worry about that. Okay. Now this is going to happen when time is going to come into picture.
Okay, sir. Okay, sir.
Okay. And
Sir,
to
for this,
alleviate that, you have to take beta such a way that beta or whatever the coefficients are there, they should be such a way that they will not disqualify these conditions.
okay, sir.
Okay. So we'll
Sir,
come to that.
for
That
this
is on.
we should use forward difference, sir. Do you by
For
dt.
this particular, we should go for forward difference because to find out the value at this new location, unknown location, I know only the nth level value. This is my n plus 1. Okay. Suppose now my n plus 1 is this. Then suppose this is n plus 1. For this, suppose let this is n plus 1. Then which scheme? Forward difference, backward difference, central difference, which scheme?
Central. Sorry, sir. Backward difference.
All three, isn't it? All three are possible, isn't it? All three are possible because when I'm saying this n plus 1, this is a known value. So I can use this n plus 1 minus n, okay? Or I can use the backward difference as n plus 1 minus n only, but in a backward sense, okay? So that we'll see. Now central difference, can you use central difference? Suppose this is n plus 1, then suppose this is n plus 1, central difference is also not likely, isn't it? It is also not likely, isn't it? But suppose my uh, point of calculation is this one and this is n minus 1. So in central difference, n plus 1 minus n minus 1 should come. So in essence, this should be my point of evaluation, isn't it? So we can write like this. In central difference, you can write n plus 1 minus whatever the value is there, n plus 1 minus un minus 1 is possible. But here it is not possible. Here you have either in n or n minus 2, isn't it? So here it is not possible. Here you will have n and n minus 1, n minus 2, un and un minus 2. For BD, for backward difference, that is also not possible because you are calculating this value with this, but then it will be something different. Okay, it will be something different. This is also possible. Backward difference is also possible here. N plus 1 minus un, that is also possible. This is already possible. n plus 1 minus un. Okay. So these two are possible, but central difference is not possible here at this location. But here it is possible because when you are here, you know these values, previous values. All values are known. When this is unknown, all other values below that unknown value are known. So n plus 1, n minus 1 is known. So un plus 1 minus un, now you can use central difference here. Okay. So when you want to use central difference, you should know this point. That is also meaning. You should know the value of this previous point. Okay. And this previous point, at least you have to calculate from any of this forward difference, backward difference scheme. You got this, what I'm trying to say here?
Yes, sir.
Okay. So the scheme to be used depends upon the point under consideration and the information available below that point. Okay. Okay. Now we'll move to this FD and BD. Now what I said here, okay, here you should have written this thing. It's like UN and UN minus 1, isn't it? It should have written like UN and UN minus 1, where UN will become unknown and n minus 1 will become known. But by definition, we are saying that always n is a known. Okay, so that is the reason we are not writing un and un minus 1. Please remember this. Huh? Otherwise, you will come up with one, this is a unknown. So even if I write this thing and un minus 1, what do you mean that this is unknown? So it should be essentially by this definition, this should be actually n replace n by n plus 1, n plus 1. Here you replace n by n plus 1. So n plus 1 minus 1 will become un plus 1 minus un. Isn't it? So it is the same thing. This or this, they are same thing. And they are same thing because we are saying that n and n plus are, n is a known and n plus 1 is a unknown. So here when I am saying un and un minus 1, it means that this is unknown and this is known. But we cannot use two different notation for the same meaning. So you have to follow the same notation. That is the reason they look similar, FD and BD, but they are different. Now we'll see what is the difference between them. And that difference is called as implicit and explicit formulation. Okay, implicit and explicit formulation. Okay, before that, before going to that implicit and explicit formulation, I would like to take a Taylor series in. Now we are talking about time also. Taylor series in two variables. In two variables, t and x. Okay. So now when two variables are involved, so how do you write, suppose temperature T at I means space and N represent a time. How we can write this? So Taylor series around Tn is nothing but equals to Tin, isn't it? There is no Taylor series expansion behind this. So this is not our interest. So either I want around Tin, this is n plus 1, or in the same Ti, I might be interested in n plus 1, okay, or in the same, I might be interested in I minus 1, this one, n plus 1, but I minus 1, this is also possible. I may be interested in Ti n plus 1, like that, okay, or only n, but I plus 1, and I minus 1. Such conditions will be there. Okay, such conditions are possible. Okay, so let us take one condition where only uh, I is remaining same, but n plus 1 is changing. So this you can write. So this is nothing but I and I remain same, but what you are saying is that around I, around n, tin, around this tin, I want to find out tin plus 1. So only the variable is del t. Still, this is not a two variable problem. Now, when this two problem will become two variable problem, when I want to find out the value of ti nearby, I mean, as well as around this ti, not only the n plus 1 value, but also some nearby I plus value. So say I plus 1 value, tn plus 1, I plus 1 value. Now this become a two variable problem. Taylor series of two variable, because I want tin value near, I mean near around this tin, I want tin plus 1 as well as I plus 1, tin plus 1 as well as I plus 1. This value I want. Okay, this value I want. So this value is around ti is delta t times and delta x times. Okay. So the value at this point is a function of delta t as well as delta x. So two variable problem. So that, so what do you say is that whatever value at this, so first value is ti. So we write ti n plus, then let's say x. So plus delta x, del t, del x, del t, del x in x. Okay. Then plus delta t, delta t, del t, del time. Now plus combination of these two. Combination of these two, maybe you can say in a diagonal manner. So delta x, delta t, twice delta x, delta t, 2 factorial, that will give you delta 2t, delta x, delta x, delta t. Plus now second order term is delta x square, curvature term, delta x square, 2 factorial, del 2t, del x2 plus delta t square, 2 factorial, del 2t, del t2. And likewise, you can add many other terms. You got this? How we are doing? Now, suppose any one of these is like this, I minus 1 and n plus 1. Now, this we can write again as ti n. Now, its delta x is minus, so minus delta x, del t, del x, and delta t is still plus, so delta t remains plus, delta t, del t, and now here one of the term delta x is negative, so negative multiplied by positive, negative, so twice delta x, delta t 2 factorial will become delta x, delta t only, but still I am writing twice delta x, delta t 2 factorial, del 2t, del x, del t, and these are square terms, so negative square of negative is still positive, so delta x square 2 factorial, del 2t, del x2 plus del t square 2 factorial, del 2t, del t square plus other terms. Okay, so you got this, how to do? Okay, so suppose you have t I minus 1, n minus 1, what it will be? What it will be? Ti n, next Tell me.
Minus delta x dou t by dou
Minus
x.
delta x dou t by dou x. Then next term
Minus delta t
minus
dou t
delta
by
t
dou x.
dou t by dou, and then now both are minus minus. So minus minus
Plus plus 2 delta x delta t.
plus 2 delta x delta t 2 factorial dou 2t dou x dou t. Now here plus only, isn't it? Okay. So likewise, you should be able to do three variables also. If it is a three variable problem, then again third term will come. Suppose there is a delta y is also involved. I j minus 1. Then here there another third term will come. That will be minus delta y del t del y. Likewise here terms will keep on coming and signs will keep on adjusting according to. Okay. What's the time now? So see, Viknesh and all other students, I need at least 3 hours in this coming Saturday. Is it possible?
Yes, sir.
Because next week I will not be here. So I want to finish these 3 hours now itself, because when I come and then finish, then it will be very close to your exam. So that is not good. It will be loaded. So let us finish on Saturday. So what can be a convenient time for all?
Sir, anytime in the afternoon,
Yeah,
if possible.
afternoon, but what is the time? So everybody should say that,
Oh,
let us start with 3 o'clock.
sir, after two,
Yeah, after
two,
two.
sir.
Sir, 2 to 5.
Yeah, 2 to 5. That is fine. 2 to 5.
Yes, sir.
Okay. So 2 to 5, Saturday. Anybody is having any problem? Other students? 2 to 5, Saturday, this coming Saturday, we'll be having this uh, computational heat transfer course. Okay, class.
Sir, so next week there won't be any CHT classes.
Yeah.
Okay, sir.
Okay, then,
Yes, sir. Thank you.
just a minute, I'm coming.
Sir,
Yeah.
hello, sir.
Okay, then, so, uh, so that is the reason we are finishing these things, 3 classes early. Uh,
Hello, sir. Excuse
uh,
me, sir.
uh.
Sir, sir, if I am not unable to attend this class, sir, so can I get that video record, sir, so that I can refer later also? Because at 2 to 5,
You
not.
actually, I don't record, so because while recording, my system gets very
Oh,
slow. So while teaching and recording simultaneously creates a problem to me.
sir, a student can allow me record
Then
that as a lecture, sir.
you can record on your site, right?
Okay, sir.
You install a software which is called as desktop recorder. Whatever the
Yes, sir.
classes you are attending, it will automatically record.